So, having seen previously how to do integrals in 3 dimensions in Cartesian coordinates, let's now consider how to do integrals in other kinds of 3-dimensional spaces. And we begin with something that looks kind of generic, but will save us a lot of work in the individual coordinate systems we'll study. And that is to say, let's continue our analogy of going from parametric curves to parametric surfaces, from 1 parameter to 2 parameters, now to parametric equations having 3 parameters of the form shown here, where x, y, and z are each of them functions of the 3 parameters u, v, and w. As we now vary u, v, and w, these trace out volumes, 3 parameters, 3 degrees of freedom, 3 dimensions. So these equations will trace out volumes in the Cartesian space x, y, and z, and we call these volumes parametric volumes. This can be thought of as a generic alternate coordinate system, and so we'll be studying two, both cylindrical and polar, and so we'll first solve the general case and then show how the same apparatus can be used to derive cylindrical and polar coordinates. But any set of equations, x being a function of u, v, and w, y being a separate function of u, v, and w, and z being a third function of u, v, and w, technically defines an alternate coordinate system associated with the parameters u, v, and w. So if we're going to integrate over such volumes, we're going to need to, as usual, cut the volume into small pieces, and that will be done by cutting u, v, and w each into small pieces and constructing Riemann sums over the contributions of each of the small pieces of u, v, and w. And so just like when we did surface integrals, we needed to calculate a typical area element associated with delta u and delta v. Here we will construct the volume element, delta v, associated with small increments in the parameters u, v, and w, called delta u, delta v, and delta w. So it's a very similar process to what we did before. The picture and the analysis will be a little bit condensed. So say here is our small region of space associated with an increment in the parameters delta u, delta v, and delta w. So let's say that here is some point associated with the parameters u, v, and w. We'll call that point O. Then if we change only u to a small amount u plus delta u, we get a new point called A here. And we've seen that this is can be linearized to be approximately equal to r0, the vector associated with the point O, r0 plus the partial derivative of r with respect to u times delta u. This is the linearization of the equation r about the point r naught. So that is our first point. If we now change only v by a small increment delta v, we get a new point r of u, v plus delta v, comma w. And we've shown that that is approximately equal to, in the linearization, r naught plus rv times delta v. And that's this point B over here on the other side. Finally, if we change only w by a small increment delta w, we get a third point, C. And again, the linearization of that function means that C is approximately r naught plus partial r partial w times delta w. Now, let's also label these, the differences between the points A and 0, B and 0, and C and 0 can be labeled as vectors. Little a, little b, and little c vectors. And little a is going to be the point A minus the point O, and they have each a common factor r sub 0, which will cancel, and we'll be left with just ru, partial r, with respect to u times delta u, approximately. I guess this should be an approximate sign. B, the vector from 0 or O to capital B, is likewise r naught plus partial r partial v delta v minus r naught, or rv times delta v. And similarly, the vector C is the point capital C minus the point O, which is r0 plus rw minus r0, giving us just rw times delta w. So that gives us approximately these three vectors, and in the limit, as delta u, delta v, and delta w become small, these linearizations become accurate, and these descriptions for a, b, and c become accurate as well. Furthermore, as those increments go to 0, this whole volume becomes well approximated by a parallelepiped. The sides become roughly straight, although the vectors need not point at right angles to one another. Nevertheless, we can calculate the volume of that object using a relationship from far back in the course that you were asked to remember, that the volume of a parallelepiped with three sides given by vectors a, b, and c is equal to the magnitude of the scalar triple product of those three vectors, which in this case gives us r sub u cross r sub v dot r sub w times the three scalars delta u, delta v, delta w. Finally, as delta u, delta v, and delta w all go to 0, then delta v goes to 0 as well, and the increment notation of the Riemann sums gets replaced with the infinitesimal notation of the integral, and we obtain the volume element. Delta v becomes dv, and delta u, delta v, delta w become du, dv, dw, and this object here in the middle, this scalar triple product magnitude, remains the same. So here is our formula for the volume element in terms of the geometric properties of the coordinate system, these partial derivatives of the position vector with respect to the three parameters u, v, and w. Now you may also recall that we had a sort of a shortcut for computing this scalar triple product if we take these three partial derivatives and we write the x component, y component, z component of the u partial derivative on the top row. That would be xu, yu, zu. Then we write the second vector on the second row, xv, yv, zv, and the third vector on the third row, xw, yw, zw, that the scalar triple product equals the determinant of that matrix. And this object right here has a special name. It's called the Jacobian. So if you ever encounter this again, the phrase the Jacobian means I have three functions, x, y, and z, three variables u, v, and w, and I take one derivative of each function arranged in this manner, and that matrix is called the Jacobian. Sometimes the matrix is called the Jacobian, sometimes the determinant is called the Jacobian, sometimes it's called the Jacobian determinant, but roughly what you typically want to do with this object is take its determinant, and so you'll often just see it called the Jacobian. So, for any coordinate system that can be written in terms of three parameters, here is a way of calculating the appropriate volume element, dv. In this same lesson, we'll apply that to one non-Cartesian coordinate system, cylindrical coordinates. So these are just an extension of polar coordinates in the z direction. So as in polar coordinates, x and y are replaced by r and theta, and z is completely untouched. Z, just as in three-dimensional Cartesian coordinates, remains the distance above the xy plane, but just like in polar coordinates, r is the distance from the origin, now the z-axis. It's just at any point in space you calculate the distance to the z-axis. That would be like this right here, is r, and theta is, if we take this point and we project it down into the xy plane, theta is the angle between the x-axis and the projection of the point. So r and theta, just as before, z now the vertical direction. And it's worth stating at the beginning what are the possible values of r, theta, and z. So r is traditionally positive. You can define a location. If given a negative value of r, you can define that location. You could say, for instance, that if in this picture we let r be negative, then it would be going back this direction. But if we're defining a coordinate in space, we always choose a positive value of r, because if I wanted to be over here, I could just increase my angle to get over there and reach that same point with positive value of r. So in cylindrical coordinates, as in polar coordinates, r is typically considered positive. Theta then goes from 0 to 2 pi, not including 2 pi, because 2 pi is the same as 0. It's periodic in theta, and once I get to 2 pi, I've wrapped back around to 0. And so if we're choosing a coordinate, we typically choose a value of theta between 0 and 2 pi. Finally, z, as in Cartesian coordinates, can be anything between negative infinity and infinity. But if you're going to be choosing bounds for integrals, it's important to respect these conventions when choosing those bounds. The equations of cylindrical coordinates expressing x, y, and z in terms of r, theta, and z. If this is our projection onto the xy plane of our point, then this is the angle theta, r, this is x, and this is y, and by basic trigonometry, this is a right angle. We have that x equals r cosine theta, y equals r sine theta, just like polar. Z is, of course, untouched. It remains itself. We can also get from the Cartesian coordinates back to the polar coordinates using slightly more tricky relationships. We know that r squared is x squared plus y squared by the Pythagorean theorem, and so r is the square root of those two. And looking at this figure, we can see that theta is the arctangent of the fraction y over x, although we have to be careful because arctangent only returns something between minus pi over 2 and pi over 2, so most calculators and computers actually have a function a tan 2 y comma x, which accounts for that fact and always returns something between 0 and 2 pi. So that's the coordinate system. Let's figure out how to calculate the volume element for doing three-dimensional integrals in cylindrical coordinates. So we simply take this definition. Our three parameters can be thought of as r, theta, and z. These three equations right here. We take the r derivative first, cosine theta, sine theta, 0. We take the theta derivative next, negative r sine theta, r cosine theta, 0. And we take the z derivative last, 0, 0, 1. We then calculate the scalar triple product, which is the determinant of this matrix, which is pretty easy to calculate. It's just 1 times this minus that. So r times cosine squared minus negative sine squared, and the cosine squared plus sine squared theta become 1, so we just get r. So dv is just r dr d theta dz. This is not at all surprising because it's just basically polar coordinates plus z, which is a Cartesian variable. So here is our polar dA, and then times our Cartesian dz gives us our volume element dv. So, two quick examples involving a cone. We have here a cone of radius capital R at the base and height h. And we're asked to find first its volume. Now, we're going to need to know this line right here. And this line gets us from the point z equals 0 when r equals 0 to z equals h when r equals capital R. So this line has a slope z of r. It has a slope h over r, capital H over capital R, rise over run. And so it also has an intercept of 0, z equals 0 and r equals 0. So slope-intercept form says that z equals capital H over capital R times little r. Now to parametrize this cone, we need to choose bounds. So we see that capital R, we can think of, we see it goes from 0 to capital R. Theta, of course, goes from 0 to 2 pi. But if we let little r go from 0 to capital R, then we have to express the z bounds in terms of r. And the way to do that is to choose the lowest value first. We see that it goes from h over r times little r to capital H. So we have to respect that h over r times little r to capital H. If we had just sort of naively chosen 0 to capital H over capital R times little r, which can sometimes be our tendency because many integrals start with 0, but if we had just assumed that, then we would be calculating the volume underneath this cone and not the volume of the cone itself. So that is not what we want to do. We need to be very careful with these z bounds and choose that. We could also have chosen z goes from 0 to h, but then the bounds on r would have to depend on z. They would go from the z-axis out to the line given by r equals capital R over h times z by taking this equation and solving for r in terms of z. So either one of these would be fine. They would both give you the correct answer. I've chosen to do it this way. Perhaps this one would be easier since it starts from 0 and goes to some value. That might be slightly less work. But I've done it the way I've done it. So first, calculate the volume of this cone. Volume, using a volume integral, is of course the volume integral of 1 dV. I integrate over the volume, the quantity 1 unit of volume per unit of volume. And that will give me the total volume. And then it's just a matter of setting up the integral. So the triple integral becomes integral from 0 to pi, theta from 0 to 2 pi, little r from 0 to capital R, and z from h over r times little r to capital H. The integrand is then just 1, and the volume element becomes r in this order, dz, dr, d theta, so that our d terms are in the right order for the integrals, working our way inside to outside. Then we just have to do these 3 iterated integrals. We integrate first in z. The integral of r dz becomes z times r. We treat r like a constant, and so we get z times r. And then we have to evaluate that at z equals h, and z equals h over r minus little r, sorry, h over r times r. That gives us hr minus h over big R, r squared, dr d theta. This is now just an integrand with only r in it, and that d theta, I suppose even at the very beginning we could have taken that d theta out into its own integral, but now we are integrating over only over a rectangle in r and theta with constant bounds on our integrals, so we can separate the integrals. The integral of d theta from 0 to 2 pi just becomes theta from 0 to 2 pi, and this second integral becomes 1/2 r squared minus 1/3 over r cubed from 0 to r. We plug in here 2 pi to get 2 pi, and here capital R to get what will be 1/6 r squared times 2 pi gives us 1/3 pi r squared h, which is exactly what we expect, 1/3 base times height being the volume of a cone. So using the same object, let's do some other integral. Let's do a real volume integral of density, given that the density is given by a function z that we just picked at random. So suppose the density equals z. We now want to calculate not the volume but the mass, which is the integral of density dv. Same bounds, because it's the same object. Rho is now z, 1 is replaced by z, and the volume element is again r dz dr d theta, as for any problem in cylindrical coordinates. Everything is very similar, except now we have extra powers of z. So when we integrate zr in our triple iterated integral, when we integrate that with respect to z, we get 1/2 z squared r being treated as a constant. We pull out that 1/2, evaluate at z equals capital H, subtract the value evaluated at capital H over capital R times r, and now we do the same thing. We evaluate our theta integral separately. The integral of d theta is theta from 0 to 2 pi. The integral of this quantity gives us 1/2 r squared minus 1 over 4 r squared r to the 4th, evaluated from 0 to r. Of course, we have that common h squared term. We now make this to 2 pi, and we evaluate and subtract. This becomes 1/4 r squared. 1/2 times 2 pi gives us just pi, and so we have 1/4 pi r squared h squared. So a similar formula, but now is different because the density is not constant within the cone. The density depends on z, with most of the mass up by the top large wide part of the cone. This is the heavy part of the cone, the dense part of the cone, and this part of the cone down here is very light. So the mass now depends to a different power on h.